Добрый день, друзья. Hello, thank you for coming. We are going to talk today a little bit about how strings are represented on the Java platform in the real world, some problems that are involved with the way we use strings, and then I'll introduce some tools that might help you deal with string encodings and string data in your own applications. Okay, so let me make sure this is going. There. Okay, so basics about me. I have been at Red Hat for about 5 years now. We have been basically tasked or sponsored to continue working full-time on JRuby. Been doing JRuby development for the past 10 years. So we managed to find an array of companies that have been willing to sponsor our work. Been very thankful to Sun Microsystems, Engine Yard, and now, of course, Red Hat for keeping the project going. And there's my basic contact information. So, JRuby. For those of you who don't know, JRuby is an implementation of Ruby on top of the JVM. And in the process of developing JRuby, we've had many challenges to deal with. Of course, it is a dynamic language, and we would like to make Ruby run as fast as possible. That means we have to do a lot of interesting tricks. We have to use newer features like invoke dynamic. We have to do our own lazy compilation, our own optimizing. So there's a lot of work to be done there to make Ruby run fast on top of the JVM. We also have to be able to integrate with native code. Ruby grew up in the C world, in the Unix world, where people are used to being able to call out to dynamic libraries, to standard POSIX functions. So we've had to do that sort of integration too. Process management kind of comes along with that. Ruby used for a lot of sub-processing, scripting, and so on, and we've had to work with better libraries than Java Lang Process and Process Builder. But the one I'm going to talk about today is the fact that regular Ruby, C Ruby, supports many different character encodings at the same time. And in order for us to be fully compatible with Ruby, we've had to follow suit and build support. All right, so here's what we're going to cover today. I will give a brief history of string encodings, where we've been, where we're going, some of the challenges and problems that have come up along the way. We'll talk about how strings and characters are represented on the Java platform, which most of us are fairly familiar with, so we won't spend too much time here. And then we'll compare that to how strings are dealt with in Ruby and JRuby, and what we can learn from that. And then I'll introduce a couple libraries that hopefully you can use to be more efficient in dealing with multiple encodings, different character data from different languages, and avoid some of the problems with the JVM strings. Okay, so strings and encodings, we'll start off here. So what is a string? Well, most of us know generally what a string is. Conceptually, it's a finite sequence of characters. Now, usually, on most platforms, this is just represented as a contiguous array, an array of bytes that may be represented as characters, or UTF-16 16-bit areas. This can also be represented in other ways. There can be a tree of different arrays. Some of you may have heard of ropes as a different way of representing strings. When you append to a rope, you just add another limb to that tree. When you want to walk the string, you walk the tree in order, and so it can be a more compact representation. Sometimes it's even represented as a list. Erlang is sort of legendary in not having the most high-performance strings, because most strings in Erlang are represented as actually a list of characters. So memory representation-wise, walking the string can be a little bit less performant than other platforms. We might have mutable strings, as in Ruby, or immutable strings, as in Java. In general, most new languages have accepted that mutable strings is generally not a great idea. There's too many concurrency issues to be dealt with, and all sorts of possibilities for you to step on other threads. So most platforms do immutable strings now. And accessing individual characters out of those strings might be constant time, or it might be an O of n access time, for example, with the UTF-8. You need to walk all of the previous characters to get to the nth character. In the case of, for example, ropes, it may actually be O of log n. You actually need to walk a certain amount of the tree to get to the character you're looking for. So what is a character? We're talking about characters here. What is a character? Well, if you are just using a computer as a normal user, what you probably think of as a character is just the glyph, the actual thing you see on the screen. As programmers, or as folks that work with character encodings, we might be interested in a grapheme, which is the individual pieces of the characters. So you may have a base character and diacritic marks that go on top of it, or combinations of two characters to make a new one. Each of those individual pieces is a grapheme. But what we're generally talking about here today for a character is one or more graphemes in combination. So represented as a single code point, a single character in Unicode tables, and so on. And this is generally not tied to a specific glyph. The idea of this is a representation of some language's character may have many different representations. For example, different fonts, different ways of displaying a particular character. Those are all different glyphs that represent the same character as a result. So early representations of characters and strings were fairly limited in scope. They would focus on one language, one particular encoding. Often these were single locale, so we'd have only one language that could be represented in a given character representation or a given character encoding. And so this led to various issues as we started to have more and more a mixing of characters from across languages. There's also many different ways to encode character data now. There's also different single byte ways, multi-byte ways. We'll jump into that and see what the problems are we're dealing with here. So first of all, we'll talk about the various single byte encodings. This is where things really got started. So of course, this started off with ASCII, the American Standard Code for Information Interchange. Around 1963, this was first published as a standard and hasn't changed a whole lot over time. So this is a 7-bit encoding. The 8th bit is not used in the original ASCII and in standard ASCII. So we're talking about the lower 128 values of an 8-bit byte. And interestingly enough, this is actually a large contributor to why bytes have 8 bits, because early character representations were using 7 bytes. 7's kind of a weird number to work with on computers, so 8 bits became a byte. If we'd started off with 16-bit characters, a byte today might actually usually be 16 bits, but history has chosen its path. As I mentioned, this hasn't been changed much, so the ASCII we have today is basically the same ASCII we've had for the past 30, 40 years. And everybody's familiar with the standard ASCII tables. And because it's been around so long, many modern encodings have tried, sometimes failed, to be compatible with ASCII. If you can't be compatible with ASCII, you may have a whole lot of other problems with interop and dealing with other systems. Now the problem here, of course, is that this is the American interchange format. This is the representation of the Latin character set, and really just the Latin character set as used in the United States and Great Britain and other English-speaking countries. And so we needed something more to represent different languages around the world, of course. So then that led us to the different ISO 8859 encodings that I'm sure some of you are familiar with these. So the idea here was that we could utilize the high 128 bits of a byte to represent an additional language. Again here, emphasizing that we want to maintain compatibility with ASCII. It's been around for a long time, but we have more character sets that we want to be able to represent. So we're talking about variations on Latin, Latin languages with different symbolic representations and different diacritical marks, non-Latin scripts, such as Cyrillic, of course. The Thai language is actually represented as an ISO 8859 encoding. And in general, this worked pretty well for languages that had a finite alphabet, a smaller alphabet that would fit into these 128 values. But for most Asian languages, we couldn't do it. There were early Japanese encodings that would only encode katakana, for example. And if you know anything about Japanese, that's only 1/3 of the character sets involved. We need hiragana and we need the kanji as well. We also had some early mistakes, such as this one. So this is ISO 8859, an early attempt to represent Cyrillic alphabet. And it was very much focused on, at first, Russian, and then they added a few more characters here and there, but we're missing a few. So Ukrainian character G is not in here. Oops, we made a mistake. As a result, ISO 8859 became a footnote in history and was not really ever used that much, because if you wanted to represent all Cyrillic languages, you did not have all the characters that you actually needed. So obviously we've got a problem here. Single byte is not enough. If we look at this table, there's really nowhere else to put it in these 127 or so values. We need uppercase and lowercase, and we've filled up most of the table. So single byte is not enough. Of course, ASCII is just Latin. That's a problem. The ISO encodings improve on this somewhat. We can have Latin plus some other character set, but what if you need even more than that? What if you need an additional alphabet, a Greek alphabet, for example? Now we don't have any good way to represent that text all as one encoding. And then, of course, there's the languages with too many characters, Asian languages, Chinese, Japanese, Korean, that may have thousands of different characters that we need to represent. Certainly no way to fit those into a single byte language. And then it continues on from there. We've got archaic languages we want to represent. We've got music and mathematical symbols, different types of pictographs like emojis. And probably the worst of all, if you happen to pick the wrong encoding representation or you don't know what encoding some text is in, you end up getting things that look like this. How many people have seen this before? Of course, of course. So this is the first few lines of War and Peace in the original Russian. This is encoded in Windows 1251 encoding, but when I bring this up in Vim, it tries to interpret it as ISO 8859-1, which is a European Latin and Latin variations. And obviously, it means nothing now. It's completely garbled. So we need to kind of guess and try a few different encodings to figure out which one's the correct one. So this is also a huge problem with the single byte encodings. There's no easy way to tell which one you're using at any given time. So what do? We need more space. We have to move to multi-byte encodings. So early attempts to do multi-byte encodings were, of course, done for the Asian languages, which really had no way of representing them in a single byte at all. So hiragana and katakana already are 46 characters each. So that's already pushing the limits of what we can fit into a single byte. Hanzi, kanji, there's thousands of characters. I think at last count there was something like 150,000 Hanzi in Chinese that were recognized by Chinese government in Mandarin. So certainly can't fit that into a single byte, and maybe not even two. Yes, over 100,000 in Chinese. So typically there's only about 2,000 to 7,000 of these considered mainstream, but we're still well beyond what we can fit into a single byte. Now a lot of these early multi-byte encodings like ShiftGIS, Big 5, the GB encodings in China, they are still in use today. They all have some representation of variable width characters. Sometimes they're ASCII compatible and sometimes not. So that can be a very difficult thing if you're dealing with both an Asian language and with Latin character sets. Some of these are actually mandated. The GB encodings in China, if you're going to release any software in the People's Republic of China, you need to support the standard GB encodings, the Guobiao encodings from Mandarin, as well as anything else you do. So this is something that just isn't going to go away. We have to deal with all these different encodings. And but perhaps the worst problem with these early versions, they're all incompatible with each other. So we can't actually translate from one to the other very easily. They don't sit nicely and match up binary-wise on the file system. So there's a problem here. What we really need is one encoding to rule them all, one representation of all encodings. And of course, what am I talking about here? We're talking about the great Unicode that's going to save us all from character encoding hell. So the original Unicode started out as the Unicode Universal Character Set. This was the ISO 10646, if you're interested in the ISO number. This has been developed in tandem with the various Unicode representations and encodings over the years since 1991. This is basically just a standardized set of character code points, a big table of all the characters in the world with a unique number assigned to them. This does not include the inter-character relationships. For example, ligatures, where you combine two characters together to make a new one. The direction that you write scripts in. For example, Arabic and Hebrew being right to left instead of left to right. Not represented as part of this. This is just the characters. Sorting. That depends very much on each language. So this is the list of characters. The behavior of sorting according to a particular language's rules is not included here. So the earliest encoding of UCS was UCS-2. The UCS-2 encoding, which used 2 bytes, so 16-bit characters. Of these, 14 bits, so this solves many of the problems of single byte, but there are additional issues here. So we have 16,000 characters we can use, because a couple of those bits are used for control characters and other special characters in the representation. We have constant access time. That's great. So we can jump into the string at any point and get the nth character without having to count all the previous ones. But like I say, it introduces other problems. All of the Latin character set wastes an entire byte. We can represent the Latin character set in 7 bits, so we're wasting a high byte for all of those characters. It's not compatible with ASCII. Of course, this is a 2-byte encoding, can't be compatible with a single byte ASCII encoding. And of course, at the time, it was only contemporary languages, languages that were currently in use. And as a result, there's a lot more characters than we can fit into 16,000 even. We had to introduce encodings like UTF-8 to represent UTF-8 and UTF-32, the idea of surrogate characters to represent more than 16,000, and now we lose constant access time. So we're making trade-offs all the time to support all these different character sets, but we still have problems. So what a mess this is. We have to deal with all these single-byte encodings. Single-byte encodings are much more efficient. The most efficient way to represent any language that has an alphabet that can fit into 1 byte, but we can only do 1 or 2 alphabets at a time. If we pick the wrong encoding, we get bad text. And of course, we don't have any good indication which encoding to use. Multi-byte encodings solve some of those problems, but are not necessarily efficient for all character sets. They sometimes over-unify. In the Chinese languages, the same characters will be the same. Different characters from the languages will be the same code point. They mean 2 different things in Chinese and Japanese, but 1 character in UCS. And these problems, unfortunately, aren't going away. The number of hands in here showed how many people have had to deal with bad single-byte encodings getting into their system. We need some way to solve this. So let's look at what we have in Java. Okay, so strings in Java are a character array and generally a length representation to say how many characters in there are actually being used. In the beginning, this was UCS-2, just like the unified character system. And you know, the idea, again, with the standard UCS-2 was that 16 bits per character should be enough for everything we want to do. And then, unfortunately, most other languages would waste that 1 byte. When UCS-2 turned into UTF-16, Java had to follow suit. We didn't have a way to represent wider characters. It was set in stone at that point. So Java became UTF-16 language. We also had this issue of the surrogate characters. We wanted to be able to have constant access time into a Java string, but now with some of the larger sets of kanji in Chinese or Japanese, with emoji, you have to actually still do a walk of all characters to be able to find the nth one. If you are just jumping into the middle of a string and that string has any emojis in it, you're going to break characters in half. That's a sad story on the JVM right now, but that's the way it is. And the real problem here is we're just kind of stuck with this. So the best we can do to represent characters on the JVM is UTF-16. And honestly, this might be the worst of all worlds. So let's take a look at this. So every time we're dealing with character data from a system, a database, a file system, whatever, we're going to have to encode back and forth. So we have to read it in from bytes, turn it into Java characters, deal with it within the JVM, and then write it back out again. And now this is frequently going UTF-8 characters from the system to UTF-16 in Java, and then UTF-16 back out to UTF-8 again. So it's all pure waste along the way. This is a large part of the performance gap that we have with C and C++. They're able to deal with raw byte characters in various ways. This also is a performance gap with Ruby in some ways. Ruby can deal with characters more efficiently, and I'll show how that works a little bit later. Of course, there's the problem with ASCII waste. This is now trying to be addressed in Java 9 with this feature, compact 7-bit strings. So all of the 7-bit strings in the world, all of the ASCII range characters, still require a full 16-bit char on the JVM. And that means we're wasting we're doubling the amount of memory necessary to represent them. Java 9 starts to address this. It packs those types of strings down into a byte array when it's able to. But if you go beyond the 7-bit range into, for example, an ISO 8859 encoding, we go right back to a multi-byte encoding again. So we really don't have any choice. We're stuck with this. It's UTF-16 or nothing on the JVM. But perhaps we have another solution for you. All right, can we do better than this? Can we do better on the JVM than just UTF-16 strings? And I would like to point to the example of how Ruby handles strings, and maybe we can learn from this. So strings in Ruby, instead of having a character array, what we have is a byte array, which represents our character data. We have a length that says how many of these bytes are in use, and we actually have an encoding as well. So every string in Ruby can have its own encoding. We can represent it as the original content from a database, from I/O, from a socket, and whatever. As a result, the text that you read in stays the same in memory. We don't have to go back and forth to a particular character representation. We don't have to do that transcoding logic. It sounds a little complex. Every string in the system could have its own encoding, but it has actually worked out very well. We only decode and encode and change the character encoding when we need to. Usually we can just leave it in its original format. So that's less copying. We don't have as many copies into a character array and back out again. We don't really have as much waste when we're reading in from outside of the system. It's more efficient in memory than single encoding strings. So if we want to represent all of our strings in memory as an ISO 8859 encoding, we can. We don't have to force it into UTF-16 or 32 or whatever else. If we want to use UTF-8, we can. We can have all of our strings represented as UTF-8 in memory. And for JRuby, what we actually decided to do, rather than try to shoehorn Ruby's strings, make Ruby's strings work in Java, we went with the Ruby way. So all of the character logic that is in C Ruby had to be duplicated for the JVM. We had have to implement a full set of encodings, so all of the ISO encodings, all of the different Unicode encodings. We needed logic to convert from one encoding to another as part of this, and we had to implement this on the JVM too. Strings and I/O need to be encoding aware. So if you're reading in data from one encoding, we need to be able to convert it to the other. There might be an external encoding on the file system. For example, Windows 1251 for representing Cyrillic scripts might need to be read into UTF-8 or back again. We might have applications where we want to leave the character data as the same as it was in memory, but still be able to deal with those strings together. And we've implemented all that logic as well. We had to implement a new regular expression engine that could work with any type of encoding. On the JVM, we have one regular expression engine, and it only knows how to do UTF-16 strings. If you want to do a regular expression match, you need to decode those bytes into characters, deal with the text content, and then probably write it back out again as UTF-8 or something else. So our regular expression engine supports all encodings. Whatever the encoding of the string is, you can still do regular expression matches. And this all works together very well. We can have mixed encoding systems, efficient representation in memory, much faster I/O and dealing with the external system, and we've turned this all into Java libraries that you can use in normal applications. Okay, so let's take a look at the libraries that I'm going to talk about here today. The first one, which is just kind of a sidebar here, a footnote here, is Byte list. So the Byte list library may be the only Maven project with a single Java class in it. Byte list is essentially a string buffer for bytes. I know I've wanted this for a long time. We basically implemented it for JRuby. So all of the typical string buffer operations that you do to grow a character array, you can now do with a byte array. But there's more than that. We have a byte array, a length, and an encoding. So we can also deal with encoding independent characters, do all of this logic that I talked about with one string has its own encoding and another string has its own encoding, all as part of byte list. So it's a representation of bytes plus an encoding, and it hides all of the difficulties for you. Here's the places where you can go get this if you want to try it. All right, so that's byte list. That's just kind of our utility class for representing a growable array of bytes. The first major library I want to cover is called JCodings. So JCodings is a set of character tables and logic for dealing with those characters. So we have things like going from a code points, UCS code points to bytes and back again, different encodings, of course. Walking characters over a given array of bytes. Since some characters may be variable width, we handle all the logic of knowing where the next character comes, so you can parse strings in any encoding using this library. We can validate whether the string actually all has correct character encodings and tell you when we've got the first character that doesn't work properly without actually going into Java strings. And of course, taking a byte array in one encoding and converting it to a byte array of another encoding directly, rather than passing it through a character array in the middle. Again, here's the contact information for that. So encoding support. I mentioned we support all the encodings from C Ruby. So that's all of the different UTF formats, UTF-8 through the UTF-32, big endian and little endian. All of the ISO 8859 encodings. And this actually includes several that the OpenJDK does not provide. I think ISO 8859.11 is not provided by OpenJDK. We have that support in our library. We also support all the different Asian encodings, so ShiftGIS, EU-SAJP, the GB encodings from mainland China, the Big Five encodings from Taiwan. You can deal with these characters and deal with this character data in its raw form. You don't have to decode it. You can just walk the characters, deal with it directly in place. And then, of course, all the IBM and Windows code pages and several dozen other different representations of characters that are out there. You can deal with it directly and not have to convert it into Java characters. More possible in the future. As additional encodings come up, as there's new ways of representing characters, we can certainly add to this. It's designed to be extendable. So we'll walk through some basics of using this library. So we've got some UTF-8 bytes here. We might get these out of a database. We might get these off of a socket, reading from a web request or something. But somehow we get some UTF-8 bytes. Now, normally in Java, if we wanted to deal with this as characters, we'd need to convert it into UTF-16, of course. But here, so we've got UTF-8 bytes. In this case, it takes 7 bytes wide to do these 5 characters. So first of all, we've got our UTF-8 encoding. We grab our singleton instance of it here. We can determine what the actual string length of the character is. So given an array of bytes and an encoding, how many actual logical characters are there in that string? We can tell what the length of a given character is. So if we're walking character by character, we know how far to advance in that byte array to step to the next character. And then, of course, we can take any character out of that string and turn it into the code point that we know on Java. So we can get it right out back into a UTF-16 character if necessary, but we don't have to. We can read stuff in from a database, read stuff in from the file system, and deal with it as raw bytes, which is almost impossible to do on the JVM without going into characters. So transcoding, I mentioned being able to go directly from one encoding to another. So we can take a byte array and turn it into another encoding directly without very little overhead, much less than if you had to do this with regular Java strings. Also, when you're reading in from I/O, if you want to take some character data in from a socket, convert it to a different encoding, and write it back out, no intermediate step involved. Generally beats the way you would do this on Java. It's pausable, so if we're reading from a stream and it turns out we've got only part of a character, it'll tell you we've got a partial character. You can read a bit more data and then continue from where you left off. So we don't break characters in half. The JVM does this for you internally, but we also have support for it as part of this library. Yes? All right, so here's an example of transcoding. So again, we get some UTF-8 bytes from somewhere, and in this case, we want to turn it into, say, UTF-16 bytes and write it right back out again. So we've got our source bytes, we've got our destination where we want to put the UTF-16. We open up a transcoder, and we tell it we want to convert from UTF-8 to UTF-16. We call convert, passing it our source and destination, the start offsets of each array, and how many bytes or characters we want to convert. And then we can take those and write them out to a database or to the file system or wherever, and we've never had to actually pass it through characters. Much faster than dealing with this on the Java platform. So there's a few bonus features in JCodings. We can do universal Newline encoding. So here we have an example. We've got some bytes that came out of a database or an I/O that has some Windows Windows line terminators in it. And we want to scrub all those out and turn them into just new lines. We've got our source array, our destination array. We open a transcoder and tell it we want to do Newline conversion. We do our same conversion process as we did before, and all different Newline types will be turned into \n instead. And there's various ways of doing this. If you want to convert everything to Windows output, you can also do that. But handling new lines for you along the way. This can also be combined with character transcoding. So you can transcode from one character encoding to another, do Newline translation as well, and it's all a single step. We can also do XML, HTML attribute and character references. So in this case, we've got a string that we want to represent as a safe string in an XML document. We've obviously got some characters here that can't be just inserted directly, less thans, greater thans, and so on. So here we're going to do decorator content for attributes, the attribute quotes to make sure that they get translated properly, and then hex character references. So if we have raw Unicode characters, we'll insert the right representation of those in XML. Again, we call our convert for our two arrays, and we can go straight through. We've got our less than and greater than, we've got our ampersand and our quote, and we've got our character references that comes out the other side. Just as part of this library, you can do this conversion directly from bytes to bytes without having to pass it through string and parse it yourself. There's also multi-stage transcoding. Most folks won't have to deal with this. In some cases, there are unusual encodings, especially some of the Asian encodings, where there's not a direct way to go from encoding A to encoding B. So we need to go through an intermediate. The worst example I found in the library is ShiftGIS SoftBank, which is a customized version of the ShiftGIS encoding for SoftBank phones to code page 50220. We can't go directly between these two easily, so we go ShiftGIS SoftBank to UTF-8 SoftBank, their custom version of UTF-8. From that to proper UTF-8. From there, we can go to code page 51932, and from there, we can finally get to code page 50220. And now, this isn't something that you have to know about necessarily, but we handle the negotiation, we handle dealing with encodings that may not be directly compatible, and pass it through any intermediate steps that are necessary. Okay, so performance. So this is difficult to compare with Java because Java has so much extra overhead and so many additional steps to do this dealing with character data. But in general, we should be about as fast to do a full character change, full transcoding change, as just one half of the Java side, the decode or the encode back out to bytes. In general, this hasn't been a bottleneck for JRuby. So if you're dealing with a lot of character data and different encodings, you probably can get a serious performance improvement by passing it through JCodings rather than passing it through Java strings. Okay, and the last library I want to talk about is JOni. So JOni is the port of a library from CRuby called Oniguruma. This is basically a regular expression engine that matches directly on byte arrays, but it supports arbitrary set of encodings. So whatever the encoding of those bytes are, you can walk them directly, deal with the regular expression directly on those bytes without turning it into some Unicode format, for example. It also has pluggable grammars. The java.util.regex library has not changed greatly, has not expanded to support new character representations, new features from the newer regular expression engines, but Ruby has a lot of nice features. JavaScript has a lot of nice features, Perl and so on. So you can use those different regular expression grammars on the JVM without even having to leave the platform. Here's the contact information for that. Okay, so why not just use java.util.regex? Well, the first obvious one is that we needed to deal with byte arrays. And there's a lot of other use cases out there where you want to be able to just read something quickly in from I/O, do a regular expression match against those bytes, and then act on it. Don't want to have to do the whole transcoding step. Don't want to have to convert everything into a character array. Much more efficient to be able to go straight to the bytes. Java.util.regex can actually stack overflow. There are certain forms of regular expression that, fed enough data, will blow the JVM stack out. And we ran into this very quickly when we tried to use standard Java regular expressions for JRuby. The case we had was Rails applications used a regular expression to parse out JPEG headers in a very long MIME-encoded stream. Fed enough data, that regular expression just blew the JVM completely up, and we couldn't use it at all. And once you get into this situation, you're stuck. You need a better way, and this library provides it. It's also better performance in general. Java.util.regex has not been updated in many years. We have a much better engine. We have our own little bytecode engine that runs on top of the JVM. So JOni almost always beats Java.util.regex as far as performance. And then, of course, like I mentioned, the different array of grammars. You have all the features from Ruby regular expressions or Perl regular expressions, and you can use them on the JVM. Oops, that jumped a little ahead. The last feature that I think is really cool, there are regular expressions out there on pretty much any engine that will run forever. It can't figure out how to match this. It's going to keep walking back and forth in the character array. It may just get stuck. Our regular expression engine can be interrupted. If it looks like you've got a regular expression that's not behaving, you can send the thread an interrupt. It'll stop the regular expression process, and you can continue on with your work. Okay, a few examples. So here we have a string pattern coming in. We've got a byte array that represents some character data. We create our regular expression. And of course, the second version here, we can pass in a grammar. So this could be syntax.ruby or syntax.perl if we wanted to use different regular expression features. We get our matcher pretty much the same way as we do in Java. And then we do our search. Starting at the beginning of the array or wherever it was specified to start, going to a particular byte, and we get our match information. Here's how we can do an interruptible version. Do search interruptible. If it turns out there's too much data or there's a problem with the regular expression, we can interrupt it and we don't tie up that thread forever. Once we got our regular expression match, we need to be able to pull our different regular expression regions out of there. So we get our region object from the regular expression, and rather than copying all of the character content out of that byte array, what we get is indexes. So we can say from this index to that index, here's where our second group matched. Now we can go directly to the byte array if we want. We can copy those bytes out, or as here, we can turn it into a string and print it out. But we can do this region matching and pattern matching directly on the bytes without doing any copying anywhere along the way. So what's the performance of this look like? Well, JOni generally is about 2 to 3 times faster than Java.util.regex for most of the loads that we've measured. And this is largely because we can avoid that decoding step. You can read bytes off of the file system and match directly, rather than converting them to Java characters. Far fewer failure cases. We'll never blow out the stack, for sure. And the cases where we need to be interrupted, where we might run forever, just don't happen as often on JOni. And again, the interruptible for the pathological cases. All right, a few more real-world examples to close this out. So let's say we have a database, and it's all in UTF-8, but we want to convert it to ISO 8859 content. Now, if we were doing this in Java, we'd need to read each piece of character data out of that database, convert it to UTF-16, then convert that UTF-16 back to ISO 8859.1, and then write it back out again. Really wasteful, lots of copying, lots of extra overhead. Here's our basic setup for our database. Everyone's done this code before. So here, we've got our UTF-8 size. So this is the width of the column in characters. In this case, the database is in UTF-8. We can get the size of that column in UTF-8 characters. Now we know how many characters we need to be able to put in our target array. So we multiply that size by the width of a character. In this case, ISO 8859, they're all going to be 1 byte. But for example, UTF-16 might be up to 6 bytes. UTF-32, obviously, it's going to be 32 bits, 4 bytes. So we can see how much character space we need to do the conversion. We've got our target buffer that we can write those characters into. And then we can open our transcoder. Let's see. So we get our UTF-8 bytes. We've got our transcoder from UTF-8 to ISO 8859. And we do our conversion directly from 1 byte array to another. Now we don't have to use the character step. We can put it out into ISO 8859 wherever we want, and we've done it in far fewer steps and less overhead than Java does. Okay, so here we have our string. We've converted it. We've got our ISO 8859 and so on. The last example here, we're going to search War and Peace, again, in the original Russian. We read our data in, and we could stream this, but we're, in this case, just going to read it all into memory into a large byte array. We've got the bytes that we're going to search for with a regular expression, in this case, just the name Pierre. We create our regular expression and our matcher based on that pattern. We do our search of those raw bytes that we've read off of the file system. And for each step, we increment the number of times we've seen the name Pierre. We increment the byte offset into the array, and then we continue. And so we've managed to do a regular expression match directly against the raw bytes without copying it all, without turning it all into UTF-16, and without having to deal with that extra overhead. And then we have our count down at the bottom. We've found the number of instances of this string, and we've worked only with the raw bytes. Okay, wrapping up here. So, concluding this here, Java's string is still evolving. We're stuck with character arrays for now in general, even though internally Java might be able to represent some types of strings more compactly. Ideally, what we might see in the future is that we can have strings that are UTF-8 internally. So we don't always have to waste those extra bytes when we've got a smaller representation of a character. And maybe even in the future, Java strings could represent characters and strings the same way that Ruby does. The truth is, and you know, you folks here probably know this as much as anybody, it's a multi-encoding world. People are going to use whatever the most efficient encoding for their language is. And so you can use our libraries to deal more efficiently with that content, to not have to deal with the extra overhead of passing it through Java strings. And you can help us work to make this integrate better with the Java platform. Maybe we can find a way to get a new string type on the JVM, or maybe we can at least improve the way that string is represented internally. And finally, the java.util.regex library kind of needs an overhaul. Those failure cases are generally catastrophic. You can't interrupt regular expressions that run too long. If you've got a regular expression that blows the stack, there's no way to get around it. So there's definitely room for improvement there. Maybe we can actually turn JOni into a JDK library as a standard library. Maybe we can re-implement java.util.regex on top of JOni, avoid some of those problems, and deal more efficiently with raw bytes as character data. And help wanted, I wanted to mention real quick. So here's all the information for the different libraries. These are a work in progress. Very interested in having folks contribute better APIs, help us with documentation. If there's features that you're interested in having, we're very open to it. This is all active work that's going on right now. And that's all I've got. Dziękuję. Thank you very much. Do we have time for a question or two? Okay. This one right here.
Thank you for your speech. I would like to clarify one thing. Whenever you need to convert bytes from one encoding to another with Transcoder API, how do you determine the length of destination byte array? Because on your example, I didn't get how do you do that.
Okay, okay. So let me see if I can go back to that example quick. Yes, this one here. So depending on the target encoding, if you have a character encoding that you're going to that has fixed width, well then obviously you figure out how many characters you have and you just multiply it by that value. In this case, we can use the max length function from JCodings. So it'll tell you what's the most size that you're going to have for any given character. As in UTF-16, you might have up to, I think it's either 8 or 6 bytes to represent all possible characters in the system. So you basically take a worst case scenario. If all characters needed to be represented as wide as possible, give me an array that's big enough. This also does have the ability, if you run out of space in that array, it will just come back to you and say, okay, there's no more room in the target buffer, I need additional space for the rest of the characters. You can make a new buffer, continue from where you left off, and continue transcoding. One more follow-up here.
Yeah, so if I understand it correctly, it means that your destination byte array might not be filled completely and might have some like unfilled padding in the end?
Right, right.
Okay, that answers.
So now this line here, this call to convert is the simple version, when you pretty much know the different links that you want. For the start arrays here, for the start indexes, the 0 and the 0, you can also pass in basically a pointer that says, when you're done, fill in this pointer with how far you got. So I know how far in the target byte array I need to start using the rest of the character data. It's a little bit more complicated API, but basically it's an out parameter for the index. And there's examples in the project that you can look at. All right.
Okay, I think that's it. So if anybody has some questions, you can ask them near flip chart.
Yep. See you out there. Thank you.